Christian Mass also joined. Hi, Christian.
Yes.
Hi.
Hi, Christian. This is the first time you're at this, isn't it?
But why did you hide it? Why did you hide it for the? I mean, I just discovered
it anymore.
Luckily, I have good friends.
You mean Jean?
Well, even better ones.
Oh, better than Jean. Wow.
No, Bart told me.
Who? Who told you?
Bart.
Ward, yes.
Oh,
that's
Ward.
right. Ward is speaking.
You don't say Ward, you say Ward.
Ward.
Okay, Ward. You know, Ward is studying philosophy, isn't he?
Yeah. He's finished. Well, what is it? He gets a PhD soon enough, I think.
Yes, a PhD. He gets his PhD soon. Wow, that's fast.
Well, soon, maybe in a year or so.
Right. Yeah. I was surprised to learn that.
Well, maybe he was also surprised.
All right, shall we get started?
Yeah,
we're very happy to have Mia Hughes. She's going to talk about rediscovering the origins of quantum mechanics.
Thank you. Thanks, Shai, very much. And thanks for having me here. So yeah, I should start with a disclaimer that I am not an expert in quantum foundations. My background, as maybe some of you just heard, is in string theory, supergravity, octonions, and stuff like that. So this is stuff that I just kind of became interested in by fluke while I was trying to work out the best way to explain to my students who I tutor where the Schrödinger equation comes from. And I gave them some kind of hand-wavy, like vague derivation, and felt unconvinced by it myself. So then I just kept digging deeper and deeper, trying to understand it a bit better until I drove myself insane. And this is, so I want to share with you some of the things that I learned. So probably if you do work on quantum foundations, this is all old hat, or if you're a Bohmian, then maybe it's all common knowledge. But I think it's interesting to talk about some of these ideas and just hear what other physicists have to say about it. So
is here.
Give me your comments as we go and questions. Okay. So, so the plan is that we're going to sort of imagine that we are living in the 1920s and trying to invent a theory of mechanics suitable for describing microscopic particles. Because the main problem with ordinary Newtonian mechanics, even without worrying about issues like why the electron doesn't spiral into the nucleus, the one problem is that we can't continuously observe subatomic particles in the way that we can with, say, a tennis ball. So we're going to invent a formulation of mechanics that is suitable for describing this situation. And then we're cheating slightly because I already know the answer. All right, so to start with, we have to decide which version of classical mechanics we're going to use. And the sort of main versions would be the original Newtonian formulation, F equals ma, Lagrangian, Hamiltonian. But what we're going to use is the Hamilton-Jacobi formulation of classical mechanics. And the reason for that is that it is really good or ideal for describing many possible trajectories at once. And that's what you want to do when you don't know what the particle is doing. You want to think about many trajectories at once, kind of a whole ensemble of trajectories. So I'm going to assume that you know nothing about the Hamilton-Jacobi formulation and give you a lightning tour of that now. Okay, and I'm going to show you by means of an example, first of all, and it's a bit strange, so bear with me. So imagine that we have a particle and we know its initial position. So its trajectory, we're going to call it q of t, and we know its initial position at t equals 0. But we don't know its initial momentum. So we know where it started, but we don't know where it's going. And we're going to call the initial position x0. Now, something fun that we could do would be to think about for each point x at each time t after 0, we could picture what the momentum of the particle would have to have been for it to have got to that point x at that time t. So this gives us a kind of hypothetical momentum field. So the shoulda, woulda, coulda sort of momentum field for the particle. So that would just be its displacement divided by the time times the mass. And so here's what that looks like. These axes represent like the x and y axis of real space at some particular moment in time. And you know, you see the arrows coming out radially because we know, by the way, I'm assuming Newton's first law at this point. So it's traveling at constant velocity. And if we find it, say, over here, after 5 seconds, way out up here, then we know it was going pretty fast to get there. But if we find it over here, we know it wasn't going very fast. It didn't need to be going very fast to get there in 5 seconds. So that's why the arrows are growing. That's why they're radial. And so far, so good. So the interesting thing about this momentum field is that it's a conservative field. So it can be written as the gradient of a scalar field. And we're going to call that scalar field S. Now, here is, you know, that momentum field was linear in X, so the S field is quadratic in X, and P is grad S. So here are the contour lines in yellow of S. S is like a parabolic bowl in this case, and notice how the momentum is always perpendicular to the surfaces of constant S. And also, I should say, this is just a snapshot at some time t. As t increases, of course, all these arrows shrink because the particle doesn't need to have been going as fast to get to each point. S, the parabolic bowl, kind of flattens out like it's made of wet clay. I guess, actually, because I have a screen share, just for fun, I'm going to show you what that looks like with time as a variable. Can you see my other picture?
Yes.
Yes. So like in the beginning, the parabola is nice and tight, and then as time goes on, all the arrows shrink, and the bowl kind of collapses. Now you notice the surfaces of constant S are kind of emanating outwards, like wave fronts almost. And that picture is very suggestive of where all of this is going. Back to the presentation. So, okay, so there's another interesting feature about this S, which is that, so we said P was grad S by definition, but just by observation, ds by dt, when you differentiate with respect to time, curiously enough, gives us minus p squared over 2m, which is exactly the kinetic energy of the particle. And, more generally, in the Hamilton-Jacobi formulation, that's going to be the total energy of the particle. Just happens to be right now that the potential is 0. So this is kind of your first taster of the Hamilton-Jacobi formalism. And more generally, the idea is this, that S, which is called Hamilton's principal function, is a kind of like a master potential for obtaining the energy and momentum fields of a single particle or particle ensemble. So we always have that P is grad S, and that minus ds by dt is the total energy of the particle. Those are just quite true by definition. Now, every formulation of classical mechanics has to have its law, you know, F equals ma, or the principle of least action, or whatever. So the dynamical law in this case is the Hamilton-Jacobi equation, which is that it's a nonlinear PDE for S that says that P squared over 2m plus V minus the total energy is 0. So in other words, like if we were to call this part, wait, this part, if we call this the Hamiltonian function, if you like, the sort of the dynamical law of this version of the theory is that Hamiltonian equals energy, basically. That's a way to think about it. Okay, so something to note is that there are many solutions S for each potential, and it's also really hard to solve this equation. So like even just for the free particle, there are multiple solutions. So notice, by the way, that what we had just a moment ago was in fact, this S was in fact a solution of the Hamilton-Jacobi equation because it fitted in here. So, but another free particle solution of the Hamilton-Jacobi equation is kind of like the opposite one to the one we just were looking at, which is, so we started off a moment ago knowing the position but not knowing the momentum. This time, let's think about knowing the initial momentum but not knowing the initial position. So this time, let's say the initial momentum is p0, which is constant, and the initial position is unknown. So again, just assuming Newton's first law, that would mean that the corresponding momentum field is uniform, because if it has p naught at the beginning, it has p naught wherever we find it. So p naught, so in this case, the momentum field is just a constant vector field. And then it's very easy to see what S would have to be to give us that momentum field. It would have to be just some linear function, so p0 dot x. And then just plugging that, you'd have you could have some function of time at the end to still get grad S equals p naught. And then you just solve for that function of time by plugging into the Hamilton-Jacobi equation. So there you go, we found another solution there to the Hamilton-Jacobi equation in for a free particle. So this one just looks like a uniform vector field, and this time the surfaces of constant S are just these lines. And again, P is always perpendicular to the surfaces of constant S. Okay, so those are some kind of fairly straightforward pictures to have in our mind. But ultimately, in classical mechanics, we want to kind of generate trajectories. That tends to be the goal. So how do we do that? Well, it's very easy. You just we have this condition that the trajectories are their velocity. So if we call the trajectories q of t, the velocity of the trajectory is always equal to 1 over m times grad s at each point, basically. So we just get this ODE to solve, and it's it's often okay. So just doing that for our S's that we found so far, for this, the one where we know the momentum, we would get, taking grad S, we would just get P naught, so 1 over M, P naught equals dq by dt. Easy to solve that, that equation, even for me. Then you get this x naught as an integration constant. On the other hand, if we take our first solution for S and take grad of that, we get this velocity field that we had before, and then replace x with q, and then you get this thing. This time, we get the same trajectory, but this time, interestingly, 1 over m p naught, which I just called that, is the integration constant, whereas last time x naught was the integration constant. So there's interesting kind of duality going on already, where like we have this known position, unknown momentum, known momentum, unknown position, and the kind of trading places in terms of the way that the variables appear. Okay, so these are just free particle examples. So I feel like I have to put in one non-trivial example. So here's the harmonic oscillator. I'm not going to go into detail. I'm mainly showing it to you to point out that although the Hamilton-Jacobi formalism is perhaps the most sophisticated view of quantum mechanics, it's also the least, of classical mechanics. It's also the least user-friendly. And just solving the harmonic oscillator is quite a challenge. So as an exercise for the reader, or if you have a look at the slides afterwards, check that this is a solution, or even find this solution. Then take grad of it and then solve the equations of motion, or rather, sorry, this is just 1D. So just take d by dx of it and solve this equation of motion. You get some pretty fiddly differential equation. And eventually you can show that it's oscillating. So it's kind of a tough one. Okay, so the next couple of slides are just an aside, just to point out what the relationship is with S and action. It's not a coincidence that S has got the symbol S. I think I'm going to actually, sorry, just bear with me a moment. I'm going to take you into my beloved GeoGebra applet for a moment again, because I think it's easier to show you this than for you to read my slide. Sorry, one sec. Okay, here we go. So to construct an S field, if you take some point in space, x0, to be your initial particle position, and then for each x and t, what you can do is solve the equations of motion, so solve the Euler-Lagrange equations, and find the unique trajectory that connects x to x0, your initial position. And then you work out the action for that trajectory and then assign that number to that point. And then you just do that for every single point in space. And then you build up this action function. So here S, this is a 3D plot of the action at each point. And so you're following the path and evaluating the action to build up an action field. I should say this is just schematic. It's not actually accurate. So going back to my slides. Okay, so that's summarized in words there and equations. So the fun thing is that once you've made that action field for S, you can show that all trajectories, for all trajectories, you'll have that the momentum along that trajectory is given by the grad of that field at that point. So in other words, P is grad S. And we also find that minus ds by dt is the energy of the particle. And a nice slick trick to see that is just to use this total derivative formula, which after some jiggling around, you see becomes, says minus ds by dt is exactly q dot p minus L, which is just the definition of the Hamiltonian. So yeah, because we're on shell, Hamiltonian equals energy. So you can say that minus ds by dt is the energy. Okay, anyway, that was just an aside. So this S, we can think of it as, it has units of action. It's very closely related to the action. Okay, so as advertised in my abstract, there is, we're gonna derive a kind of version now of probabilistic classical mechanics, which looks extremely suggestive of quantum mechanics. In fact, it's almost the same in many respects, except all the important ones. So as I said earlier, because we don't have access to initial conditions for microscopic particles, we can't just, you know, like with a tennis ball, you say, I threw it this hard in that direction and it finished up over there. We can't make that kind of before-after kind of continuous observation here. So it makes sense to use the Hamilton-Jacobi formulas where we can think about many trajectories at once. And it also makes sense to encode our ignorance or our knowledge, if you're an optimist, of the particle's position in a probability density function, which I'm going to call rho. And since the particle can't teleport, rho must satisfy the continuity equation. So, which essentially just, I guess everyone knows that. So that means that our theory has two equations of motion, which are coupled. It has the Hamilton-Jacobi equation for S, and this other equation for rho, the continuity equation, which also includes S. Oh, I should say, by the way, that remember, 1 over m grad S is just the velocity field. So rho times that is exactly the probability current, the probability per unit area per second. So that's why it looks like that. Now, both of these equations can be obtained by minimizing a single functional. Now, this is somewhat ad hoc. We're just doing this because it works. This thing I, which is defined as it is here. Just ignore the lower line for a moment. This thing I is just rho times kind of the contents of the Hamilton-Jacobi equation. And so if you think about what that is physically, it's basically the expectation value integrated over time of the Hamiltonian minus the energy. So what we're doing is we're essentially saying that the average difference between the Hamiltonian and the energy is minimized over time. That's the physical principle, which leads to and the S and rho that do that, which minimize that I, are exactly those that satisfy equations 1 and 2 here. So in other words, using the Euler-Lagrange equations on S and rho from this, starting from this functional, we get equations 1 and 2. So you can think of this as just a way to sort of roll both of those two equations into one. And this is, by the way, following the method in Schrodinger's original paper about his equation. So, okay, so another thing we could do that's just for fun with these two equations is combine them into a single complex equation, because why not? It'll save us some space. So we could very reasonably, we could make S and rho the real and imaginary parts, but it makes more sense to make S the phase, because it's only defined up to addition of a constant. So if we were to add like 2 pi to it, then it wouldn't affect things. I say it's only defined up to addition of a constant because all the physically measurable quantities come from derivatives of S. On the other hand, rho is, because it's a probability density function, it's always greater than or equal to 0. So why not make it the modulus, or the modulus squared, of this complex, this new complex field? So now I'm going to make a leap, which is I'm going to define a function psi, which is root rho e to the I s over h bar. Now, for now, h bar is just a constant with units of action. I've just called it that because things will look more quantum if we do. And so I'm going to give you some reasons why that would be a reasonable choice. Well, as I already said, we know we can add a constant to S and rho is greater than or equal to 0. But perhaps more interesting physical reasons. Well, there's an interesting analogy with optics going on here, which is that rays of light in optics are always perpendicular to wavefronts, aka surfaces of constant phase. And here we have classical trajectories always perpendicular to surfaces of constant S. So why not make S a phase of some wave? But it's even deeper than that, because there is the Hamilton-Jacobi equation is literally formally identical to an equation from optics called the iconal equation. It's literally the same equation, only the iconal equation is talking about the phase of an electromagnetic wave, and this is talking about some particle thing. So why not start thinking about S waves where S is the phase? This one is trickier to justify. Now I'm trying to justify the root row. Well, the best thing I could come up with so far was that in the photoelectric effect, we know that sort of photons arriving per second, so that would be the photon, like intensity of photons is proportional to the amplitude squared. So why not try and mimic that here in this situation? And there's number 4 is kind of a boring one. It's just a technical change of perspective, which is that when you're solving the Hamilton-Jacobi equation, you usually use additive separation of variables. If we do this, we'll be using multiplicative separation of variables. Maybe things might ease up in terms of how difficult it is. Okay, so our new protagonist is psi, and it's root rho e to the I s over h bar. Now some cool stuff starts to happen, which is that, well, actually, first I have to tell you something else, which is a beautiful fact in its own right, which I could talk about for a while, which is that if there is a space-time symmetry with a generator T hat, then the corresponding conserved Noether quantity is T hat S. So this is something which you can show using the Hamilton-Jacobi equation. It's very straightforward little proof. So let me give you some examples then. So for example, translations are generated by the derivative, the spatial derivative operator, or I guess grad if you like, and momentum, which is the quantity conserved corresponding to translations via Noether's theorem, is grad S. Energy, which is the conserved quantity associated with time translations, is given by ds by dt, or minus ds by dt. And angular momentum, which is the conserved quantity associated with rotations, is given by the generator of rotations acting on S. Again, so it's really nice pattern that appears, which is why I call S like a master potential early on. It's kind of like, you want to know what the conserved quantity is, you just act on S with the generators, which is extremely elegant, I think. So, and something really cool happens when we put S as a phase, which is that now when we act with minus IH bar times those generators, we get the quantity associated with those generators coming down. So it kind of looks, so when we act with minus IH bar times the translation operator, we get P times e to the IS, and similar for these other ones. So we get something resembling eigenvalue equations, eigenfunctions and eigenvalues, but of course these P's are functions right now, they're not constants. So it's worth asking what about eigenfunctions? I'll come back to that in a moment. Now, also interesting, remember this is all classical, is that the expectation values of position, momentum, energy, and angular momentum, they all take this particular form, this operator sandwich form where psi star operator psi integrated overall space. By the way, I think every integral in this talk is overall space, in case you're wondering. So the first one, it's easy to see why. Second one, it's kind of easy to see from what we just did, but bear in mind that there is going to be a derivative of rho term that comes out of this as well. But it just happens that that's a total derivative, and same for the next one, and same for the next one. So actually we end up with just what we would expect for these expectation values, rho times that variable integrated over space. So there's this peculiar feature that these expectation values have this form of this basically inner products in a vector space. Like we have some function, some linear operator, and then that function again integrated over space.
Maya,
yes.
1 second.
Yeah.
So couldn't this be another reason why you took the square root? Because
yes, that's a
if you
good
hadn't
point.
done the square root here, it would be rho squared, and then you would say, oh, well, this doesn't look right, so let me go back and take the square root.
I guess that's true. but you're somewhat biased there by thinking that you know what you want to see. I guess, but you're right. Certainly, this pattern emerges when we pick that square root. Yes. So yeah, I said earlier on. What happens when with eigenfunctions of these operators? Well, let's just think about classical eigenfunctions just for fun. What's the physical interpretation? Well, if t hat is a first order differential operator, as it has been in all these examples, then we're going to get, when we act with minus ih bar t hat on psi, we're going to get, just using the product rule and the chain rule, and a bit of fiddling around, you see you get this. So for psi to be an eigenfunction, we'll need t hat s is constant, lambda, and we'll need this term to vanish. So we'll need t hat acting on log rho to vanish. So for example, if t hat was if minus ih bar t hat was the momentum operator, we'd need rho to be independent of x. If it was the time translation, sorry, if it was the energy operator, we'd need rho to be independent of t. So physically, what this means is that eigenfunctions correspond to a kind of a wave function where the measurement of t hat s is certain to give a particular value, lambda, but we also have no knowledge of the corresponding conjugate variable. So even something vaguely, I mean, there's no reason in this version of the theory to think that these eigenstates are important, but it's just interesting to look at them. Okay, and finally, the cherry on top, when you put these two, so I've just rewritten the continuity equation in this particular way. When you put the two of them together, so make this the imaginary part and this the real part, you get this equation, which is the classical Schrödinger equation. And it looks extremely familiar, but it's got this ugly nonlinear term in the middle. For that reason, there is, the equation's nonlinear, there's no superposition principle. We don't have linearity. The sum of two solutions is no longer a solution. So all the kind of like wave-like effects that we might, hope to see in a theory that explains things like the double slit experiment and electron diffraction won't happen here. But I mean, when I first saw this, it blew my mind that this equation exists even in the classical.
You said that it won't happen here because the equation is nonlinear.
Oh, yeah.
Wouldn't it be more appropriate to say it won't happen here because we know the dynamic is equivalent to classical mechanics?
Well,
you
that's
having a tiny nonlinearity, a very tiny one here, it would be nonlinear, but you still have interference.
Yes, you're absolutely right. Yeah. Yes, that would be a more proper way to say it. I guess in this context, that is manifesting itself, perhaps in this nonlinear term, we could say. Yes. Cool. So we're so close to quantum mechanics, we can reach out and touch it, and it's going to be very easy to do this. So we're going to follow our noses and say, well, we know we want to explain stuff like the double slit experiment and electron diffraction. So we want a theory with interference. We want a superposition principle. That would work if this equation was linear. So why don't we just get rid of that, that crappy term? And that's it. It's the Schrödinger equation. And now this might not seem very satisfying, but let's try and interpret what we've done. So right now it's just formal. But let's try and see if we can make sense of what this means, crossing out this term. And remember, we're inventing new physics now, so it's okay to change things. So
wouldn't you? Sorry, can I just ask a quick question? Wouldn't you expect shouldn't you be able to take a limit of h bar in order to
I mean, the trouble is that h bar is everywhere.
Yeah, it's just that it's squared, like it seems backwards somehow, because I would have expected that like somehow like the thing that makes it classical, that seems to be like as h bar shrinks, that's getting smaller faster, so it seems backwards.
Yeah, you're right, it seems backward. It kind of is backward. So if anyone is familiar with like Bohmian mechanics, you might recognize that this is the term this is basically proportional to the term that's called the quantum potential, and it shows up in the quantum version of the Hamilton-Jacobi equation. Right now it's showing up in our classical version of the Schrödinger equation. So it's kind of there, it's the thing that is making it quantum. Here it's the thing that's making it classical. So it is kind of backwards right now, but you'll see, Cole, that shortly when we look at this in the S and rho form, it will be more like how you expect. I think the role of H bar right now is obscured by the weirdness of what we're doing, I think.
Okay, thanks.
And also remember that at this point, you know, in the very classical theory at the start, H bar wasn't necessarily anything quantum. It was just a constant we introduced with units of action. So the meaning of taking H bar to 0 right now isn't quite what it will be later.
Isn't it a bit ironic that when you cross off that quantum potential term, which you identified with Bohmian mechanics, you get rid of that term. The theory you then have is in fact Bohmian mechanics.
Yeah, well, it's kind of like you've just shoved it from one side to the other. It's like, it's the same, yeah, it's kind of.
You don't really have to shove it, just get rid of it. And then that equation together with the P equals grad S is Bohmian mechanics.
Yes, yeah, it is. It is kind of strange.
Actually, I want to just chip in one brief comment. Since you introduced the psi implicitly contains H bar here also, right?
Right, yes, that's true.
If you look at the decomposition of the Schrödinger equation into the rho part and the S part, right? So then, in fact, the H bar square only shows up in the term with a quantum potential, and then one can start arguing it's maybe small and so on. So here it's very implicit. That's why it's not so obvious what will be going on.
Yes, good point. Okay. That's a very good way of saying it. I am going to get to that version in a couple of slides time. So if that's still not 100% clear, then hopefully that it will be in a moment. Okay, so all right. So we've got our new equation, the Schrödinger equation. And now let's kind of reverse engineer I, the functional which we minimized, so that it gives us the Schrödinger equation. So how would we need to modify I to yield the new linear Schrödinger equation? Well, it's easy. You just add this one term, which is grad of log rho squared. There's a 1/2m in there and h bar over 2. And notice it's multiplied by rho here. So I'm calling the new functional IQ, I quantum. And again, so this, these terms give us the Hamiltonian minus the energy plus, so this other term, which I'm calling h bar squared over 8m, and confusingly I of rho. I'll call it script I, calligraphic I of rho. So calligraphic I is this thing called the Fisher information, which is something in stats. And it's a kind of measure of information. And I don't really have time to talk much about it, but I'll talk about what it does in this context in a moment. So actually, weirdly enough, so we get some like term that is a thing from stats, talking about which measures information content in a probability distribution function. We'll come back to it in just a moment. So varying that, so finding the equations that minimize I, Q, we get some equations of motion, and they are the quantum Hamilton-Jacobi equation, which has this quantum potential term in it. and just the ordinary continuity equation. And these two real equations are now following our same prescription as last time. Psi is root rho e to the I s over h bar, give us the Schrödinger equation. So in this context, it's clear that taking h bar to 0 will kill off the quantum term and give us back our classical. But yes, it was a really good point. That the psi contains h bar, so you can't really take h bar to 0 until you've kind of expanded out that dependence. Okay, cool. So let's get into the question that we're all interested in, which is what is this? What's the deal? What's up with the new term? So the new term is a functional of rho, which is, I think, is very interesting because it seems like, you know, bearing in mind these are all terms, these are all energies, it seems like we've added an energy which corresponds to the shape of the probability distribution itself. Earlier on in our old theory, rho was just something that parameterized our ignorance or our knowledge, and it had no, you know, it doesn't have energy. It's just a thing that we are like, you know, an abstract tool that we're using to help us keep track of where the particle is. But now it has energy, and I would say that it looks as if this breathes life into rho and ascribes some kind of physical reality to it. I put maybe because, you know, I said I'm not an expert in quantum foundations, but I'm just saying how it looks. So into the nitty gritty then, the really cool part is that I of rho, this term, the Fisher information, it is large when rho is tightly peaked around the mean. So it's a functional, it depends on the shape of rho. And when rho is tightly spiked around the mean, it's big. And when rho is loose, it's small. So for example, if rho is a Gaussian, I of rho is 1 over the variance. So in other words, the sharper the spikes in rho, the more energy assigned to that term. Now specifically, that energy takes the form of momentum. So this is a lot of equations on this slide, so bear with me. So we have to assume something new in this version of the theory, or at least if we're going to agree with modern quantum mechanics, which is we have to agree to interpret the new term as a contribution to the momentum, which makes this true, a contribution that makes this true. Okay. Now, this wasn't true in the classical theory, I have to say. Sorry, px here means the x component of the momentum, and the subscript q means in the new quantum theory. So this clunky notation means the square of the x component of the momentum, the expectation value of that in the new theory and the new quantum theory. Now that is equal to this operator sandwich, which, if you know modern quantum mechanics, seems reasonable. That's the momentum operator squared. But we have there's no obvious reason to interpret it like that in our current theory, which is why I'm saying this is an assumption. If we expand out this second derivative and get rid of some total derivative terms, so do some integration by parts, then we find we get two terms. So we get basically the momentum squared in the x component of the momentum squared, and then the log rho derivative squared. Okay, so in other words, we get the old expectation value of the momentum, px squared in the old theory, that would be this first term, plus the x part of the Fisher information. So which is this ix is just like what we called I of rho would be ix plus iy plus iz. Something I forgot to write down was that the Fisher information has this really nice property, which is that if you have a joint probability density function for, like, say, x, y, z, then it's additive. So you get that the Fisher information is just the sum of the Fisher informations of the product rows. So, okay, so what's going on here? Well, it seems we have a new contribution to the expectation value of px squared, basically. And that new contribution is that's the new thing in the theory. The new contribution is this Fisher information thing. So as the probability density function becomes more spiky more spiked around the mean in the x direction, the momentum squared in the x direction gets bigger, or the expectation value of it gets bigger.
Should it be clear at this point what's meant by calling this an additional contribution to the momentum? That would actually require understanding what's meant by momentum.
Yes, that's a very good point. So when I say, I guess I should probably add the words an additional contribution to the momentum expectation value. Yeah, you're right though. I should say to the momentum expectation value. I'll add that in before I upload the slides. So you're right that we don't know in the local sense as in point by point, we have no idea what momentum means in this version of the theory. But we do know but we do know that, in accordance with our observations, that this equation holds, and therefore that there is some new contribution to the momentum squared expectation value.
So maybe I chip in a little bit.
Yeah.
I think what Shelley wants to point out is that, of course, the first term is literally what, even in classical statistical mechanics, you call the ensemble average of the generic momentum of a particle. You cannot say that for the second term. It's more like an entropy term. It only depends on the rho. On the other hand, you correctly pointed out already that in this story now, rho is no longer a passive quantity like it is in classical statistical mechanics. So what you called, there's somehow life in it, right? So therefore, it's more that the what you call the quantum expectation value of the particle momentum can be written as two contributions. One is indeed the expectation value, an ensemble expectation value of a quote unquote classical momentum type quantity, plus something that is in addition to that. And it's not the momentum of a particle, it's somehow associated with that damn field rho, right?
Yeah, exactly. Yeah, it's somehow, it comes up in our measurements, but we don't really know what it is. We know it's going to appear when we measure p squared, this term. Yes, thank you for that. Yeah, exactly. It's important to be careful with my words here because some of the interpretation is fuzzy. So I'll try to not say anything that's not true, at least. So remember the expressions I had for the expectation value of momentum and all these other variables back here. That was true in the classical theory that we had before, but it's also true now. So we can say that pxq, the expectation value, is still the same as what it would have been were that term 0. So we can say that the variance in the new theory is by definition it's this, and just looking at what we've got above, that means it's the variance in the old expression for the variance plus, so yeah, the quote unquote classical variance plus this Fisher information term. So you can see where this is going. It's going to the uncertainty principle. Like we're finding that the spikier the rho, the more p squared and the more delta p squared we find associated with that when we make a measurement. So let's just finish that off formally. So we had that delta, so delta px, the variance of the momentum in the quantum theory in the x direction is this. So that means that there's a lower bound on that variance, and that lower bound is the Fisher information in that direction. But on the other hand, if you know anything about Fisher information, which I barely do, you might know that there is this inequality called the Kramer-Rao bound, which in this context, in this special case, says that delta x, the variance of x in the x, sorry, the variance of the position of the particle in the x direction, times I of rho is always greater than or equal to 1. So that gives us this inequality if I times everything by h bar squared over 4. And then just looking at the above, that gives us that this is greater than or equal to h bar squared over 4. So you see we get the uncertainty principle. And in a sense, arguably, like, that is the new thing almost that we've done, is that we've said when we measure p squared, the tighter the probability distribution, the bigger the answer we get, and that, you know, that's exactly you know, giving us the uncertainty principle. It's a kind of a different way to look at the uncertainty principle without thinking about operators or Fourier transforms. Okay, so I could write tons about this, but I already filled up the screen, so I just stopped. But the final slide then, the possible interpretations of this new term. I mean, I don't really know what different people would say, but in every context, but I guess Copenhagen might say something like, were it a person, the new term is the missing piece of the puzzle, that it's precisely the bit that is needed to make the Hilbert space and operator formalism work. And that somehow, you know, and that the bringing in the uncertainty principle is part of that.
Could you say again what you mean by the new term?
Oh, yeah. Well, I guess I kind of mean different things in different contexts. I mean this term we added to our functional, or if you like, the new term in the Hamilton-Jacobi equation, which comes from that term in the functional, or I guess you could also think of it as this this contribution to p squared. In it, I mean, each time the term is different, but the it's kind of the origin is the same.
But let me also interrupt. Sorry.
Oh yeah, please do.
Because
please do.
The point is, in the standard orthodox approach, you can of course say, oh yeah, that's the difference between the classical Hamilton-Jacobi variational principle and the variational principle for the Schrödinger equation. But there's also an omission. It's not only that you add something on the level of the Hamilton-Jacobi formalism, you drop the guiding equation for the particles. So basically, you assume that particles don't actually have positions and don't move. That's also part of Copenhagen. And then, of course, all hell breaks loose. De Broglie-Bohm, of course, says, no, why should you drop the guiding equation, right? And that's everything becomes objectively clear.
Right. Yes. Yes, that's an extremely important point, which I definitely should have said. Yes, exactly. Yeah, that we. I mean, in this next bullet point, I'm saying that in the de Broglie-Bohm version would be to say that new term in the Hamilton-Jacobi equation is actually a potential. So giving rise to a new force, and we still have trajectories, because why wouldn't we? Because it's just like the same theory, but with an extra term, and the trajectories are given by the same equation as before.
Exactly.
And by an extra term, but once you've rewritten the Hamilton-Jacobi equation with the extra term, the classical, you know, with the thing involving rho, the extra term, once you've rewritten, you made it quantum by linearizing it, getting rid of the nonlinear term and getting a Schrödinger equation. You've got Bohmian mechanics. You don't need to say anything more. You don't even need to think about an extra term. Bohmian mechanics is there instantly. Contrast that with what you have to do to get to standard textbook quantum mechanics at this point. You have to do the song and dance about operators. You have absolutely nothing whatsoever to do via the Bohmian, if you want to end up at Bohmian mechanics. Yeah,
it's very true. I mean, I'm still slightly, I should come clean about my own opinions here. I'm still kind of on the fence as to interpretations, because, you know, I find very interesting that the fact that the Schrödinger equation is linear. I mean, maybe someone has something to say about this, about the fact that the Schrödinger equation is linear, And, you know, it's interesting that this extra term, which appears in the new deeper theory, is exactly the one that is needed to make that equation linear. And you know, is there some physical significance to that linearity other than, I mean, we know it generates the interference, but you know, I wonder whether that makes something makes sense about the operator formalism. Although I am definitely very skeptical of the standard textbook version of quantum mechanics. But I guess I wonder whether there's something in the operators because of this this linearity. I don't know what anyone has any thoughts on that.
I don't know about that, but I would say that however you might have, however undecided you might have been about what version of quantum mechanics you prefer before you did this, it would seem to me that after doing this, the appeal of Bohmian mechanics should be much stronger.
Oh, it undoubtedly it is. It absolutely is. I mean, no, it totally is. And you know, another thing I should add is that even if you're the staunchest Copenhagen supporter, I mean, something I find very frustrating is that they kind of just like would just pretend that these trajectories are like just don't exist, but like you could write them down in the ordinary Copenhagen quantum mechanics. I mean, you can take grad of S and find the integral curves, like that's fine. And you get some interesting paths. What do they think they mean? Just nothing at all? Like
They think they mean nothing at all, I guess.
Yeah.
Except when they're convenient.
Yeah, exactly. So yeah, no, I'm absolutely, no, I think I am absolutely way closer to Bohmian, but I think I'm just a bit too hesitant to fully get on board. I'd say I'm about 80% on board. Anyway, that's not interesting. So,
but that's pretty far.
It's pretty far, yeah. I mean, I guess the other thing is that I don't really know what to do so much with quantum field theory next. Anyway, so some other possibilities worth mentioning, things that I've been, you know, getting very into is the possibility that the new term maybe represents some kind of rotational motion, or like the Zwitterbewegung, the jittering motion of the electron, or something like that, and even that the fact that we complexified the Schrödinger equation might somehow be an element of Clifford algebra, representing that rotationalness, maybe like a Clifford bivector or something like that. And I've got some references if you want to read more about these things, if you don't already know about them. And another possibility is that it's some kind of stochastic term representing maybe some kind of like Brownian diffusion type process, or the jittering of space-time. These things have been written about in all kinds of places, but I've just mentioned the names of the people who I've referenced. So an interesting thing to add about that, you know, diffusive process is that if you have just like an ensemble of particles described by a density function rho, then by Fick's law of diffusion says that the particles flow away from the high density regions and into the low density regions. And you would actually get that the velocity of the particles is like grad of log rho. So that extra term we added really looks kind of a bit like what you would see in a diffusive process, but it's you can't quite interpret it as that. This doesn't work out. Anyway, right, so I'll stop rambling. That's the end, and thanks for listening. I'm sure it was old hat to a lot of people, but I hope somebody learned something. I did.
Well done.
Thank you so much. Let's unmute ourselves and thank Maya.
Thank you.
It was a fascinating talk, Maya. Thank you so much.
Thank you.
You're welcome. Now we are opening the floor to have more discussions and comments.
Yes, please. Go for it.
So I think maybe someone has asked you all this before already. So what do you have thoughts about the relativistic version of this?
Yeah, I've looked into it a little bit, but I mean, it gets pretty complicated pretty quickly as soon as you start trying to combine it with relativity. So I guess for those people who haven't seen the relativistic Hamilton or even any Hamilton-Jacobi formulation, I should say that, well, you notice, I'm sorry, I'm looking for the, here we go. You notice there's something very relativistic about this, right? We've got P is grad S and minus D by dt is S. We've even got that minus sign in there, as we might expect for an index up momentum. So you, in fact, the Hamilton-Jacobi equation, yeah, generalizes very nicely, but as soon as you start trying to do, I mean, I guess it's similar to the complications that arise when you try to do any kind of relativistic quantum mechanics. There are issues with causality and propagation outside the light cone and things. And honestly, I being relatively new to most of what I've got here, so I can't really say a huge amount about the relativistic version. I just know that it's tricky. Maybe I should ask the floor.
Well, some of us have some thoughts on that, but I agree that it is a puzzle.
So Maya, can I make a comment about
Yeah, please do.
relativistic extension? So I think a lot of what you do formally generalizes to classical field theory in the Hamilton-Jacobi picture, say for a scalar field. So if you wrote down classical scalar field theory in the Hamilton-Jacobi picture, you could end up formally deriving or recovering a classical functional Schrodinger equation, and then deleting this quantum potential, functional quantum potential term, and then get a functional quantum Hamilton-Jacobi equation and continuity equation and all of that. And I think Peter Holland, in his book, The Quantum Theory of Motion, mentions that at some point. I don't know if you're familiar with that book.
Yeah, actually that book is my, if anyone, yeah, that's my #1 reference, in fact, which I discovered it after having sort of found most of this stuff. And then I was really gutted to discover that most of the things that I thought I had found out on my own were already old hat. Mm-hmm. But yeah, I've not got that far in that book yet, but yeah, where is it?
Yeah, so you'll probably discover that one of the things in Peter Holland's book was the basic classical wave equation that you had.
Yes, it was.
I'm not sure whether he was the first to have that equation, but
no, I think Rosen. Rosen was.
What?
I think Nathan Rosen or Schiller in the early 1960s was the first to at least write this down in the literature.
Interesting.
As far as I know. Schiller, Rosen, 1962, or maybe 59.
Yeah, they had that nonlinear equation.
Yeah.
Yeah, I was gutted to learn that that it was already a thing. I was like, oh, I'm gonna be famous.
Well, it's impressive that you came across most of it on your own.
Yeah, I mean, I guess I was kind of just working back and forth between the normal Schrodinger one and the other ones.
I have a small comment. You have a very nice derivation of Bohmian mechanics. I saw a much shorter one from Dustin Lazarovici.
Wait.
He takes a standard textbook on quantum mechanics where they're doing some, I don't know, neoclassical, what's it called, Michael? Quasi-classical regime or something?
Yeah, semi-classical.
Semi-classical, where they have the equation P equals grad S in quotation marks. Here's derivation is remove the quotation marks.
That's very good.
That's on YouTube, I think, the video of that derivation.
Yeah, an interesting. So I'm planning on writing like just maybe a little review of this, just for fun, pretty much following what I just did in this talk. But an interesting question actually is the question of, like, we said P was a conservative vector field, but why does it have to be conservative, and why can't it have a rotational element? And interestingly enough, the rotational element, so when does a particle do rotations? Well, a good example would be when it's in a charged particle in a magnetic field, and you can add a rotational component to P, and that is literally the magnetic potential. So like the way you can think of it gives you a really interesting perspective on like what the vector magnetic potential actually is. You could think of it, it's the rotational component of the P field of the particle, which is really really interesting. It took me ages to do it, but I managed to find the S and the basically decompose the momentum field for like a particle with a known initial position in a magnetic field, decompose the momentum field into its grad S part, its irrotational part, and its rotational part. And sure enough, the rotational part is the magnetic potential, and the irrotational part is the grad of a scale. Of course, it has to be, and that S. So I'd like to put that in the review. I mean, it's not really enough for a paper, but it's an interesting little observation.
But of course, you could have rotational motion, nice simple rotational motion from a vector field which has no rotation in it, like theta, angular momentum states of atoms.
Right, that's true. Yes, that's true. That's true, yeah. So in that coordinate system, I'm getting a message on the chat. Oh yeah, that's okay. That's the simple derivation.
Yeah, it's the thing that Shelley was describing.
Yes,
Your short YouTube video.
I'll watch that shortly.
But I don't think that derivation is actually published. It's just a video.
I see.
And by the way, Shelley, it's actually anonymous. You just outed him.
Really?
Yeah.
It's anonymous? What do you mean it's anonymous?
I don't think the video says that who is doing it.
He gives the video. It's Dustin.
I think he doesn't identify himself by name or show himself in the video. It's just
maybe so.
Now we know.
Maybe so. That's interesting.
Yes. So anyway, I have another comment on your references. I saw Michael Hall and Reginato in there, and so this is actually an interesting technical paper. And but there's something in your presentation that I like much better than what they do, because they actually mix up a little bit ontology and epistemology, right? So they refer to the Fisher information as really information, and then they say, this now makes clear what is the epistemological part of quantum mechanics, and here's the ontological part, right? And that's not a pretty good conceptual thing to do, to mix these up, right? So one should keep that separated, and you do that, right? So you indeed insisted that somehow we should rather think of rho really playing an active role and not being this passive epistemological thing about my ignorance. No? Why should the particle care about my ignorance, right?
Right.
So this I like much better. So
right. And why should your ignorance contribute to the energy that you measure?
Exactly. No? And, but this, by the way, is also one of the ways how I like to present when I teach the beginning of quantum mechanics, right? How one could come from classical Newtonian mechanics, right? And then stumble more or less across quantum mechanics by doing more or less what you did. No? You look at an ensemble description with Hamilton-Jacobi formulation instead of Hamilton formulation. So you have a row, And then, of course, at some point, you may ask yourself, is there something analogous to a free energy expected value, right? So what do you do in Hamiltonian statistical mechanics? You take the expected value of the Hamiltonian and you add the typical, say, entropy expression, rho log rho.
Right.
Well, when you do that, you get something that is clearly not quantum mechanics or not Schrödinger's equation. But once you play around with integral rho log rho, it doesn't take too much fantasy to also try playing around with the Fisher information and still think you're doing something like a free energy. And whoop, there's a linear equation, and people love to solve linear equations. And they may stumble across the Schrödinger spectrum for hydrogen, and suddenly, wow, what was that? And you have been thinking all the time still in statistical mechanics, and only then after the fact of doing something harmless, innocent looking, you realize that you have actually done something that reproduces effects in nature, and it is a radically different thing of what you thought you had done, right?
Yeah.
In a similar way, you can discover relativity theory by thinking you are just perturbing a little bit of Newtonian mechanics. I'm not talking about now Maxwell's equation, but just the speed limit, right? And then only after the fact you start asking what is the transformation law between what a particle is doing now and half a year from now when we are going in the opposite direction of around the sun. And it's not the Galilei transformation, and it fits experiments better. And whoa, you have discovered something completely new that you didn't think and didn't set out like this. So this is much more plausible how people can actually get into quantum physics in this case, or and then throwing it at you as a postulate that some genius had done.
No, exactly. That's exactly, I think, my main motivation and why I wanted to write this as a review, because I think when you learn something that you don't feel like you could have invented it yourself, you feel really, really stupid. And it's nice to see that, you know, if you'd been in the right place at the right time, looking at the right equation, you would have, you'd have probably come up with the same thing.
Right.
I think from a psychological perspective, it's good for everyone to
absolutely.
have that.
Yeah. I agree very much. Yeah.
You didn't mention the many worlds interpretation of quantum mechanics. Does your work shed any light on that?
That's a very good question. Do you know what? I actually thought, I wonder if someone will ask me about that. And I thought, I hope not. I don't really know. I tried to think about it, but it made my head hurt. Let me think about it for a moment. I mean, I guess in this version, we haven't really considered measurement in that way, like the collapsing of eigens onto an eigenstate or anything like that. It's hard to say at this point, I think. But I guess whatever the de Broglie-Bohm theory says about many worlds is probably what this is saying about many worlds.
Yeah, maybe many worlds fits well, maybe it doesn't. But one of the things you were struggling to do at the end was to motivate, see how to get Copenhagen out. Well, one of the important parts of Copenhagen is collapse rule, the collapse postulate. Does that come out?
Yeah, that's an interesting question. Like, well, so there is a model of that if you look in Holland's book, The Quantum Theory of Motion, there is a model proposed for explaining why the process of measuring will lead the state to become an eigenstate corresponding to the operator you're measuring. I can't remember the details of the model to be honest, but if you I kind of read through it. It was kind of like a magic trick where a bunch of stuff happened, and then it was like, ta-da! Here is the result. But one thing that I did think is kind of interesting is I'm not sure whether there's a way to make this rigorous, but a certain intuition I have is perhaps that like we've seen that the uncertainty principle emerges from this process, and we also saw that eigenstates correspond to states where we're certain to get a certain result for the thing we're measuring, and where we have no knowledge of the conjugate variable. So so there is a kind of connection almost between like eigenstates and the uncertainty principle, I think. And I wonder whether there's any significance to that. Like I said, I'm not sure how to make it rigorous. So to be sure of the particle's momentum, you need to have flat probability distribution by the uncertainty principle, and that kind of pushes you towards an eigenstate by these two observations. So there is a kind of there is something there, but I'm yet to articulate it fully.
I would suggest the following, though. I really do think that the Copenhagen interpretation is fairly hopeless as a serious physical theory, but it's very good as something which yields accurately predictions about results of measurements. So one shouldn't try to make sense of everything in Copenhagen. Just try to make sense of what is in there that does make sense. Yeah.
Yeah, no, I agree. I agree that it is pretty hopeless. I mean, one of the things that you know, I hadn't, being someone who didn't work on quantum foundations most of the time, I was shocked and appalled to learn that there are no. It's not possible to define Hermitian operators that satisfy that their commutator is I or IH bar X and P. Like that if you do that carefully, you know, on some specified domain for the size, then it's literally not possible to define operators like that, and that's deeply concerning, considering that's so fundamental to Copenhagen. So in that sense, I do think there's something hopeless about Copenhagen, but I guess, like I said, I'm somewhat drawn to there maybe being some significance to the sort of linearness of it, the linear operators, the linear equation.
Maya, sorry.
Mia.
Okay. So there's a subtlety about the assumptions you have to make about the S function, I think, when you go from the Schrodinger equation, the nonlinear linear one, to the classical or quantum Hamilton-Jacobi picture, right? So in classical mechanics, S, yeah, I mean, it can be a single valued function, but it needn't be, right? It can be multiple valued, and there's no specific way, right, in which it can be. But in quantum mechanics, the S function, right, it has this specific multi-valuedness, right, that it can change only by integer multiples of 2 pi.
Yes, that's true. Oh yeah, I see what you're saying. Yes, that's true. Yeah.
So when you go from classical mechanics to the, yeah, I don't know, Bohmian mechanics, right? And that transition, seems to me you're also making additional assumptions about S, right? Or you're putting some restrictions on S.
Yeah, that's a good point. I'm just trying to think what that means. So, well, I guess that particular one, that now we can only shift S by integer multiples of 2 pi h bar, or I guess h. That it's hard to see exactly what that means, given that all of the observable quantities depend on derivatives of S. But you're right that there is some restriction there.
Yeah. So I would say what that would mean is that you have an additional you have a constraint on S, namely that the closed loop integral of grad S is
Right.
equal to n times h, or n is an integer.
Right. Right.
Something like the Bohr-Sommerfeld.
Yes, something like that. Yeah.
If you start from Schrodinger's equation and then you write psi equals mod psi e to the is and recover the quantum Hamilton-Jacobi equation and classical continuity equation, then that constraint on psi is already there, right? It falls out of the Schrodinger equation, the linear Schrodinger equation.
Yes, I see what you're saying.
Go the other way, you need to.
It doesn't matter whether it's linear or not. Psi,
Sure.
if
Yeah.
S comes from psi, then it has the property.
Right.
Yes, you're right. Yeah, exactly. Like it's that loop integral is telling you that when when you do this loop integral, you get some integer multiple of h. It's talking about when S can and can't be single value, multi-valued, and when rho is 0, S can get away with being multi-valued, I guess integrating around those points is when you find non-zero ends for that integral.
I mean, I guess what that is suggesting is that Schrodinger's equation is more fundamental than the Hamilton-Jacobi equations. Psi is the variable which gives you the right picture.
Yeah, that's a really good point. I hadn't thought about it like that.
Yeah, so basically, if you don't have that constraint on S, then this pair of equations, the quantum Hamilton-Jacobi equation and the continuity equation, are not equivalent to Schrodinger's equation.
Yes, yeah, I see what you're saying. Yeah, so you have to
solutions than Schrodinger's equation.
Right. Yeah. So it would be they're the same as long as rho is non-vanishing in that domain, basically. But if rho vanishes anywhere, then you're right that they're not quite equivalent.
And this very point that Manley raised was one of the very severe difficulties, real problem in the work of Ed Nelson, who had a derivation of Schrodinger's equation from some kind of stochastic diffusion. But what he wasn't able to really get in the derivation is the quantization condition on S. It can be multi-valued in just the right way. That doesn't come out of his analysis at all.
Interesting. Yeah, it's a really good point. I should definitely include that in my review, which is to come.
Yeah, which isn't to say there might not be some more complicated version of these sorts of theories, like Nelson's or other theories, where that condition could somehow come out, right? But it is a problem, right, that one has to address. If you want
for sure.
the other routes and make.
For sure.
But one can be comforted by the fact that we're not talking about genuine derivations here, just how one might somehow get more or less to a new theory from an old theory. You don't have to get there exactly. You just want to motivate how the new theory can be understood as arising in a not too unnatural way.
Yeah, that's certainly my motivation anyway, at this point.
Did you have the hope in doing this work that the work would actually, if you derive a theory in a fairly compelling way, you might expect at the end of the day to know what your theory actually says about the world? So
yes.
Anybody who says they can derive quantum mechanics ought to be able to, at the end of that, say what quantum mechanics says. That is, they ought to end up with a particular version of quantum mechanics.
Yeah. It's so true. Yeah, it's very, it's just so difficult, isn't it? With these few steps, it's like trying to watch the ball that's been swapped around these cups. So what is actually happening? Because the problem is that the meaning S and rho seems to have somehow changed in adding this term, and yeah, you know, maybe you could have a kind of more Bohmian perspective where it's because rho is is related to the quantum potential and is some kind of to do with some kind of field, or maybe you know, something else, but it's just so deceptive that deceptively simple that you just add this one thing and suddenly you have no idea what any of the symbols really mean anymore.
Okay, but you add this one thing and let's say you get a theory that way. Then you want to see whether you can make sense of the theory. And if the theory refers to a term like rho, which is sort of a probability, you'll say, oh, how could that make sense? How could this theory yield this probability? What do I even mean by probability? All that means is you've got some more work to do.
Yeah, well, that's true.
All right, this is certainly a fascinating discussion. We have to end at some point. Of course, the conversation should continue, and I have a feeling this is the beginning of a beautiful friendship, as and that we will have you over again, hopefully, Mia, and then we will continue this discussion. This is quite fascinating. Let's thank the speaker again.
Thanks very much.
Give me up.
Thank you very much. And next
you.
week we are going to have Ward, who's here. Ward, you want to tell us what you will talk about next week?
Sure. So you asked me to say something about Bohmian quantum field theory, right? So that's exactly what I'm going to do.
Oh, great. Oh, I'll definitely watch that.
So we will look forward to it. Thank you so much, guys, and see you next week.
Thank you. Thanks again.
Thank you.
And everybody stay safe.
You
Stay
too.
safe.
Stay safe.